So we have a tensor. And we're interested in studying the secant varieties of the Segre variety on one hand, finding equations for it. And on the other hand, we're interested in a particular tensor, the matrix multiplication tensor. And I'll discuss both today. But the last few lectures, we've been discussing general things about tensors. So we had this notion of a tensor being concise. If we look at the map, for example, here, that this is injective, and similarly, also TB and TC injective. And then we defined it to be 1A generic if, in addition, there exists some alpha in A star with rank of T alpha, so that's an element of B tensor C, maximal. And in the case that the dimension of B equals the dimension of C, if we choose bases of A, and write our tensor like this, where Aj is a basis of A, and each xj are elements of B tensor C. And let's say that this is dual to some alpha, so that x1 is full rank. So choose bases such that x1 is equal to the identity matrix. Then Strassen's equations, the local version, is that the border rank of T is bounded below by half the rank of any commutator plus the dimension of B. Now, we only saw the proof. In case of xi, xj identically equal to 0. So the first thing we'll do today is fix that. One proof of Strassen's equations in general. We used it to show that the border rank of the matrix multiplication operator is at least 3/2 n squared. And it's worth remarking, this was theorem Strassen in 1985. And as of 1985, this was the highest border rank of any explicit tensor. despite that we saw that a random tensor in CM tensor CM has border rank of T equal to, on something like m squared over 3, i.e. n to the 4th over 3 in our case. So what do I mean by explicit? I mean, we know by dimension count that the dimension of the secant variety, the Segre variety, cannot fill the ambient space until you get to about this number. So that means there must exist tensors of border rank about that number. On the other hand, if somebody hands you a tensor, you have no technique whatsoever to prove it has high border rank in 1985. In fact, you had no technique whatsoever to prove its border rank was greater than 3/2 m. That was the state of the art. So I'd like to introduce some colorful terminology from computer science. This is what they would call a problem of finding hay in a haystack. So I guess maybe there's a American expression, the problem of finding a needle in a haystack, because you have a pile of hay, and inside the pile there's some very small needle that you have to find. That's a standard difficult problem. This problem is of a very different nature. If you close your eyes and pick something at random, odds are, with probability 1, you will end up with a piece of hay. But, it could happen. You may stick your hand in and pull out a bird feather by accident or some other strange thing that found its way into the stack. And you have no way of proving that this bird feather is a piece of hay or a bird feather. So this is a very strange situation that if we close our eyes and pick something with probability 1, it has border rank roughly m squared over 3, but we can't do anything other than prove that it has border rank at least 3/2 m, that it doesn't live in the 3/2 m minus 1 secant variety. So we will slightly improve the situation. The 3/2 m situation. That will be the second thing we'll do today. And then we also saw that even if all these commutators are 0, the tensor T could still have very high border rank. Even if our additional equations, so end closedness And I don't know if we named the other one, the Segre intersection properties. We're satisfied. And the picture was a tensor that looked like this, where T of A star looked like this. And we could write T as some T1 plus T2, where this is, say, A1 times X1, where this is full rank. And this T2 lived inside a Cm-1 tensor Cm over 2 tensor Cm over 2, and it's generic in this space. And the third thing we'll do today is address that issue. So let me call that such a tensor compressible. We'll discuss equations for compressible tensors. So this is both the morning and the afternoon, probably. So at one point I was asked, are there any equations known at all that cannot be translated easily into the language of linear algebra? And this last topic for today is a class of equations that do not come naturally from linear algebra. So in some sense, it's an affirmative answer to the question. In another sense, it's a little disappointing because these so-called equations are difficult to write down. One would have to use elimination theory to write them down in general. And we can only sort of use these equations indirectly. So that when we discuss that, I'll see. So that's why I put equations in quotation marks. They sort of do what we want, but not exactly. Okay? Is there any questions on this review?
So you will explain about what is the compressible tensor.
So by compressible, I mean that we peel off a little piece and we end up with something that lives in a much smaller space.
So what is T1?
T1 is this piece, and T2 is the image of this piece. So what happens is you peel off a little, and then you're squashed into a smaller space. I'll be very precise when the time comes. But just intuitively, that causes us a problem, and I would like to address that problem. Okay? And what's beautiful here is this involves some very nice geometry of Grassmannians and vector bundles and things. Finally, I mean, I know I was supposed to be doing some algebraic geometry, and we're doing a lot of linear algebra, but we will get to at least some beautiful algebraic geometry today, and also tomorrow. Let me give tomorrow. I'll discuss geometry of algorithms. More precisely, border rank algorithms. And this is a study of curves in Grassmannians. So that's so we will get quite geometrical by the end of the week. Other questions? Okay, so I'd like to give a slightly more geometric derivation of Strassens equations. If you're familiar with determinantal equations, that is, so let me just make a general statement about algebraic geometry. So if you're familiar with this, that's great. If not, just ignore it. So one way of, if we have a variety X and we want equations for a subvariety Z, one very nice way to realize that is to have some line bundles or even vector bundles on X and some map phi between this and realize phi Z as the degeneracy locus of the vector bundle map phi. And if you think about what is a degeneracy locus, it's exactly where minors of some equations are vanishing. It's exactly these determinantal equations that we've been seeing. And what I'm going to do, but I'm not going to use this language, is show you explicitly how Strassens equations can be realized in terms of degeneracy loci. And in fact, a version of Strassen was discovered around the same time via vector bundles was discovered by Barth. So if you're a big fan of vector bundles, you can look at Barth's work. You should, if you're a fan of vector bundles, you should certainly look at Barth's work because he has very beautiful papers. But I'm not going to discuss it in that language today. I don't need such fancy language. I'll use elementary language. So let's return to the classical equation. All right, let's try the letter B today. So this is a linear map. And now I'm going to, so the earlier idea for studying Strassens equations was to take this linear map and to look at its image and study the nature of its image. The new idea is to take this linear map and make it more interesting. So we will augment this linear map by adjusting it by something. So one kind of almost trivial thing to do is tensor it with the identity map on the vector space A. So if this map had rank Q, this will have rank Q times the dimension of A. So nothing is interesting so far. But now I'm going to do something inspired by representation theory, although it's quite elementary. This we could think of as a space of matrices. We have one group acting on it. We have GLA acts on this space of matrices. And when it acts the same way on both of these spaces, so not by conjugation. So if it were acting by conjugation, we saw on the endomorphisms of A, the endomorphisms split into at least two pieces, in fact exactly two pieces, the multiple of the identity and the traceless endomorphisms. But here this is really kind of space of bilinear forms on A dual. But that also splits. This is the action G on X tensor Y, well, on a matrix, let's say capital X, acts by G X G transpose, if you write it out in matrices. And under this action, we can write X is the sum of a symmetric matrix plus a skew-symmetric matrix. And this action will preserve that splitting of a symmetric, if I have a symmetric matrix and I hit it by G on the left and G transpose on the right, it stays symmetric. If I have a skew, it stays skew. So these two spaces are preserved. So without making any non-geometric choices, I could choose to project it into either the symmetric or the skew symmetric spaces. Let's project to the skew. You could see as an exercise what happens to the symmetric. And now I can look at the composite map. Let me call this, say, T, well, I should really call it TBA, but I'm just going to call it TA wedge. And I claim that this new map from here to here might be interesting. So let's assume for the moment well, let me not do that. So if I have, if T is of rank 1, then the image of T a wedge will be what? Well, here I would take some beta tensor some AJ, and this will map to beta of B AJ wedge A tensor C. So the image of this map is A wedge A tensor C. Now this is interesting, especially if the dimension of A equals 3. Then these two vector spaces have the same dimension, because 3 choose 2 is also equal to 3. And then the rank of this, let me write it as A tensor B tensor C, a wedge, is just equal to, well, I can only, if I choose a basis, and this is A, I can only have A1 or A1, I can only have A2 or A3 here. This rank will be 2. Well, I just, T is this, right? So I take the linear map associated to this. This linear map will have rank 2. Just as if T is equal to A tensor B tensor C, then the rank of A tensor B tensor C, B, like that thing, will just be 1, right? Its image will be, because the image of A tensor B tensor C B is just, what is it? It will be C times little a tensor C. And here the image, the image, let me just write it out, is, let's say A is equal to A1, then the image will be A1 wedge A2 tensor C, the span of this, and A1 wedge A3 tensor C. It's a two-dimensional vector space. But this vector space has dimension 3 times the dimension of B. And let's assume dimension of B equals dimension of C. So we potentially get equations up to R is equal to, Well, we would divide by the rank 1, because just like here, if T is the sum of two rank 1 matrices, then the rank of this is at most twice times the rank of it for rank 1, which is to say 2. If here T is the sum of two rank 1 matrices, the rank of this map is at most 4. If it's the sum of at most 13 rank 1 matrices, the rank of the map is at most 26. So we potentially get lower bounds for border rank up to the full thing, 3b, divided by 2. So, e.g., if A, B, and C are all Cm, we choose a C3 contained in A, and we take T restricted to that C3, tensor Cm, get equations up to 3/2 m, which is what I claimed Strassen did. And now I want to show you that this is in fact Strassen's equations. At least, well, I won't give the full details, but I will give most of the details. Right. So let's do bases. So let's write T is some A1 tensor x1 plus A2 tensor x2 plus A3 tensor x3, as we were doing before. And so this T a wedge in bases, this will be a 3b by 3b matrix. And let's group it like this. I'm going to group it, here we'll do A3 tensor beta 1 up to A3 tensor beta b, then A2 tensor beta 1, so it'll be blocks. A2 tensor beta b, and finally A1 tensor beta 1, A1 tensor beta b. And down here, I'll do A1 wedge A2 tensor C1 up to A1 wedge A2 tensor CB. And similarly for A1 wedge A3 tensor suffix C and A2 wedge A3 tensor suffix C. So if I have an A3 going in, then I can only get A3 wedge something coming out. So I cannot have anything in this block. Similarly, if I have an A2 going in, I have to have an A2 wedge something going out. So I have to have a 0 in this block. If I have an A1 going in, I have to have an A1 coming out. So I have to have a 0 in this block. Now, if A3 goes in, then if A3 goes in, if I get A3 wedge A1, I have an X1 coming out. If A3 goes in and I have A2 wedge A3 coming out, then I'll get an X2 coming out. I may have a sign error, but I'm not going to worry about it at this point of the game. If I have an A2 going in, I get an X1 coming out, but actually it's a minus X1, the way I did it. An A1 coming in, I should get a minus x2, a minus x3, and an x3. So I've written it in block format. If this is my original tensor, when I represent this linear map by a 3b by 3b matrix, and these three things are b by b matrices, this is what I get. And now, let's assume, let me just use this little piece of board here. Say x1 is equal to the identity, then exercise that the determinant of this matrix is exactly the determinant of the bracket of, well, plus or minus the determinant of bracket of x2 and x3. And maybe it's twice that, but I don't care. The point is, this is Strassens commutator. So strictly speaking, I have only given you a proof for the other extreme case of maximal possible rank, the determinant. But a little more work shows that this is really equivalent to Strassens equations. Questions?
So the last theorem is A2 is 3.
Yes? There's, I mean, I wrote big C. There's really should be, you know, C1 up to C whatever.
Dimension C and B are
Hmm?
Dimension C.
That's correct. I assumed that early on. And if they're not equal, you have to take the smaller, just like here, if dimension of A was greater than 3, I had to choose a 3-dimensional subspace. Say dimension of C is greater than dimension of B, I just choose a dimension B subspace. And I get this. Okay, well, now we saw that by augmenting this map, we got something interesting. So let's try to augment this by something a little more interesting. And this will be, so we've taken care of this. Now I will go a little bit better by a slightly better augmentation. So the thing that was annoying here, that maybe not annoying, but that we might have lost some of our information, was because this was really only a really good thing if the dimension of A was equal to 3. Dimension of A is bigger than 3. This doesn't have so much information. And so we had to restrict to a 3-dimensional subspace. So what we would like is something that if the dimension of A is larger, it still gives us something interesting. So here, we'd like some kind of this skew symmetrization to work more generally. So that's what we'll do. So let's consider TB tensor the identity on lambda p of A. And again, inside this space is the space of totally skewed tensors. And I consider this map, which I'll call TA wedge P. Now, I could have put other things here and done other projections. And in fact, there's a larger theory about that. But it just so happens that this very simple thing has worked better than all the other things that we've tried. Up until now, at least. So now let's do the same calculation. Let's say T is little a tensor B tensor C. Well, then the image of TA wedge P will be equal to lambda PA wedge little a tensor little c. So the rank will be, well, this thing is isomorphic in dimension. This is like the same thing as lambda P minus P A mod A. So this is dimension of A minus 1, choose P. And again, this will work best if this dimension and this dimension are the same. So that is to say, if dimension A is equal to 2p plus 1, we get the best bound. Well, in general, the border rank of T is greater than or equal to the rank of this TA wedge P divided by A minus 1 choose P. And this number here is less than or equal to A. Let's assume P is less than dimension A over 2. So this is at most dimension A choose P times B, assuming again B equals C. And so potentially equations up to A choose P over A minus 1 choose P times B. That is to say, A factorial over P factorial P minus A minus P factorial divided by A minus 1 factorial divided by P factorial divided by A minus 1 minus P factorial. So this number is A divided by A minus P all times B times B. And this is best, I got a little ahead of myself, if A is equal to 2P plus 1, then we get 2P plus 1 divided by 2P plus 1 minus P, P plus 1 times B. So that is to say, nearly 2b minus 1. And since these numbers are integers, can get this border rank bound. So potentially, we could go from 3/2 up to 2m minus 1. Now, that's good news because that's an improvement, but it's also a little sad because we're hoping to get all the way up to m squared over 2 or 3, and we just improve the constant. But this was 1985, and this was 2012, and there was nothing in between to improve this leading coefficient in those intervening years. So at the rate we're going, it may be a while till we understand things properly. This shows just how ignorant we are in this subject.
So why you choose A is 2p plus 1?
Because I want this fraction to be as large as possible. And if I take A to be 2p plus 1, this fraction becomes very close to 2. A little bit less than 2. So again, if my dimension of A is larger than 2p plus 1, I just take a subspace of that dimension. That will give me the best bound. Just like before when we took a three-dimensional subspace. Now, there's a catch. One of the most difficult things, so I've learned a lot of interesting things from the computer scientists. One of the most difficult things is if somebody hands you a polynomial, a very explicit polynomial like we have here, the polynomial is the determinant of this. We can write it out explicitly in terms of the coefficients of our tensor. This will only work if this polynomial is not identically 0. For all we know, here, this map could never be full rank for some reason, for any tensor, even a generic tensor. Now here, how did we prove it? We proved it using matrix multiplication, the tensor we were most interested in. We proved these equations were non-trivial because they were non-trivial on matrix multiplication. I mean, you could use other tensors, but that's the tensor we used. But here's a surprise. For matrix multiplication, so P taking whatever it should be, P around n squared over 2, something like that, is not of full rank. Now, I have to apologize. I cannot give you a proof of that today because the proof uses representation theory, and Professor Kwok asked me to avoid representation theory. So I will just write proof via representation theory. But we can get new lower bounds for the matrix multiplication tensor as follows. So what I will do is I'm going to restrict to a subspace. Let me explain first a little bit more carefully what happens with this map for matrix multiplication. Maybe I rewrite the map over here so we don't lose it. So we have this T A wedge P from B star tensor lambda P A to lambda p plus 1a tensor c. And if t is equal, well, let me write it this way. Let's say t is some t I j k a I tensor b j tensor c k, where these are basis vectors. Then if I have some beta tensor some v1 wedge vp, this will map to, so this is summation over ij and k, summation over ijk, t I j k beta of bj, ai wedge v1 wedge vp tensor ck. So this is our map very explicitly, where here V's, V alpha are elements of A. Now our matrix multiplication tensor has very special coefficients. So this is a random tensor, arbitrary tensor with arbitrary coefficients and a basis. But matrix multiplication is very special. And we should expect a very special format for the map. So recall that matrix multiplication sits inside U star tensor V star, tensor W star, tensor U, and is the identity map. So this is my A, this is my B, this is my C. So this M, N, A, wedge P, this is a map from lambda P of U star tensor V, tensor V star tensor W, to lambda P plus 1 U star, no, not V star tensor W, but V tensor W star, because this is B star, to lambda P plus 1 U star tensor V, tensor W star tensor U. Agreed? Now, what does the identity map do to an element of W? Identity map eats an element of W, gives you back the exact same element. It does nothing. So this map actually, this W star is far from the action, and this map actually factors between, let's call it M, N, N1, A, wedge P, tensor the identity on W. So where M, N, N1, A, wedge P is the map from lambda P U star tensor V tensor V to lambda P plus 1 U star tensor V tensor U. And if U1, UN, a basis of U, and say mu1 up to mu_n, the dual basis, then of course the identity on U is the summation j equals 1 to n uj tensor uj, but similarly with identity on V, identity on W. And this must be a tautological map. So what does it do? It takes some V tensor. So let's let E1 up to En a basis of V. This will take V tensor some C1 tensor E1 wedge CP tensor EP and map it to, well, this map comes from the identity on U. And so what happens, it takes this V and maps it to the summation of mu J, so summation over J, mu J tensor V, wedge C1 tensor E1, wedge wedge CP tensor EP, all tensored with the corresponding U lower J. Now, as I said, this map is not a full rank, and we can describe the kernel explicitly in terms of representation theory. I will skip that today. But now, I'm going to give you a proof. So I claim if we restrict to an A prime contained in A of dimension 2n plus 1 and take p equal to n to a good A prime, the map becomes injective. And that implies the following theorem.
So what is QC? What is QC upper?
Hold on. One second. Yeah, so go ahead.
So what is QC?
The CIs are elements of U star. They're not basis vectors, they're just any vectors in U star. So I have to tell you what, so this eats any vector in this space and spits out a vector here. So I just need to name those vectors, but I can't use my basis vectors because they're playing another role. So I just write it as some vectors. Okay, so what I'm saying is if you believe the claim that if we do this restriction, we get this new lower bound for the border rank of matrix multiplication. So we improve from 2n squared, so Strassen got 3/2 n squared, and now after 25 years, we get 2n squared minus n. Now what's also intriguing is that also means there are equations for secant varieties of Segre varieties that we're aware of that matrix multiplication satisfies. So in answer to Professor Kwok's question on the first day, he asked me, why didn't I believe that conjecture? And I gave an answer that I used to think the conjecture was preposterous. But now, I don't know, because now we have equations for secant varieties of moderately low border rank that matrix multiplication, in fact, is in the zero setup. So it could potentially be in a very small secant variety, but it cannot be in one smaller than that. So I have to do a little algebra. I think, I'm trying your patience that there has not been as much algebraic geometry in this lecture series as I would have liked because I had to establish a lot of notation. But at least the proof here will use some very nice algebraic geometry, very elementary. And in the rest of the lecture series, stay tuned, there'll be some very nice geometry. So we can kind of transition to thinking more geometrically. Okay, so first of all, I need to choose a good A prime. So I want to think of, okay, there's a tiny bit of representation theory here, but it's really easy. So notice that if I look at sim D of C2, the dimension of this vector space, homogeneous polynomials of degree D on a two-dimensional vector space, is D plus 1. So let me fix. Let's write, well, I don't even need that. So let's choose an identification of U equal to sim n minus 1 C2, and I'll do the same for V. Or maybe let me write it U star, although it won't matter because C2 is self-dual as an SL2 module. Then U star tensor V is sim n minus 1 of C2 tensor sim n minus 1 of C2. And inside here, there's a very nice subspace, namely sim 2n minus, did I get my numbers off? 1 and 2n minus 2 of C2. Check my numbers. Yes, I'm going to take P equals to n minus 1. And A of dimension 2n minus 1. Sorry about that. Correction. And this has dimension n, this is dimension n, and this has dimension 2n minus 1, which is the number we wanted. So this is going to be our A prime.
Dimension n plus 1? Dimension of U is n plus 1?
No. Sim D of C2 has dimension D plus 1. Sim n minus 1 of C2 has dimension n. That's, I made a mistake earlier. Well, that's good, because now we have a map about polynomials. Now remember, if we could think of sim alpha of C2 dual. This is like the differential operators, homogeneous differential operators of order alpha on C2. That's another way to think of it. And so we have a map from sim alpha of C2 cross sim beta of C2 dual, say alpha is greater than beta, to sim alpha minus beta of C2. Namely, this is some polynomial, this is some differential operator. I just D of P. Like if this is basis xy, this is basis d by dx, d by dy, dual space. And in particular, if P is equal to some L to the alpha, and D is whatever it is, then this L to the alpha comma D will just map to D of L, thinking of it as a polynomial, L to the alpha minus beta. So I could re-exchange the roles of spaces and their duals And I can think of this as a polynomial evaluating on a point in the dual space. And then I just get alpha here. Now, instead of this map, it'll be convenient to look at the transposed map going the other way, since we just want to show it's a maximal rank. So, well, now it's restricted. So we have this transposed map. We'll go from lambda p plus 1 of sim n minus 1 C2 dual tensor lambda n of sim 2n minus 2 of C2. I should have. What am I doing? Let me write it properly. This is lambda n of sim 2n minus 2 of C2 tensor sim n minus 1 of C2 dual. And this goes to lambda n minus 1 of sim 2 n minus 2 of C2 tensor sim n minus 1 of C2. I hope I got the duals right. And so if I have some G tensor some F1 wedge Fn, this maps to summation I equals 1 to n minus 1 to the I minus 1. Let me call this map hook, D hook P. G hook Fi, tensor F1 wedge Fi minus 1 wedge Fi plus 1 wedge wedge Fn.
So you restrict your subspace A prime in the transport.
This is my A prime.
Yes.
And now I'm going to show that this transpose map is surjective.
Yes, but your original map is kind of on the U.
Right, so I restrict and I take transpose. That's why I didn't write what goes in here. So restrict and then I take the transpose. So let's let L and Lj be in C2. And let's look at the image of L to the n minus 1 tensor L1 to the 2n minus 2 wedge Ln minus 1 to the 2n minus 2. So this space here is spanned by elements of this form. So you can find any element in this space will be some linear combination of n minus first powers and things like this. So, this space is spanned by such elements because it's to the n minus first power. Such span the target. So if I could show that any element of this form is in the image of the map, then I've accomplished my goal. So first assume that L and Lj are distinct. So assume L is not equal to any Lj. And now there exists a polynomial C2 star vanishing. So this is a polynomial of degree n minus 1. So it can vanishing on L1 up to Ln minus 1 and non-zero on L, right? If we have a homogeneous polynomial of degree n minus 1, we can choose it to vanish at n minus 1 points of P1 and not vanish at the other points of P1. There, that's the algebraic geometry for this morning. Homogeneous polynomial P on P1 of degree d vanishes on d points. Then I claim that G tensor L1 to the 2 n minus 2 wedge Ln minus 1 to the 2 n minus 2 wedge L to the 2 n minus 2 maps to our element. Well, some constant that I don't care about, this L to the n minus 1 tensor L1 to the 2 n minus 2 wedge Ln minus 1 to the 2 n minus 2. And to see that, we just look at the formula. G evaluates to be 0 on every single one of those LIs. But it will not be 0 on L. And so it will be some constant times what's left over, L to the n minus 1. Because we're doing an evaluation of our polynomial G. Now, if L happens to be not distinct from one of these, then we can just take limits, argue by Zariski closure, and this gives the proof. Do I have time for some remarks? I have time for 3 minutes of remarks. So, it turned out that I should be careful here. There was 2011 that this result was proved, and it was only it was only 2 years later, in fact 2013, that I actually found a tensor for which this map was injective and showed that these equations were non-trivial beyond their non-triviality for matrix multiplication. And that's what caused this psychological change for me to think of the conjecture instead of as ridiculous as merely astounding, because there are equations. And since then, I found a lot of equations for secant varieties of Segre varieties in the range between here and here. And every single one of those matrix multiplication satisfies. I would be very surprised, though. I do not believe this is the correct answer. I don't know what the correct answer should be. So this afternoon, we'll address this other issue, these compressible tensors. And then and that'll have some nice vector bundle issues going on, but very elementary vector bundle things. And then tomorrow, we'll do geometry of algorithms. And thank you for your attention, continuing attention.